So let's solve this example 21-5. Let's read. So we have a square coil of wire. So here you see the square coil of wire with side L 5 centimeters. So each side here is 5 centimeters. That means they are giving us information about the area. So let's already write this. The area of this loop will be 0.05 in meters squared. Okay, this in square meters. What else do they tell us? You see that we have this loop, this wire contains 100 loops. So it's not just once that we go around, but we go around 100 times. So N, let's also write this here, N is 100. This square, this loop, is positioned perpendicular to a uniform uniform magnetic field of this value. So we got here two more pieces of information, that the magnetic field is 0.6 Tesla, and they also told us about the angle, because they say that this field is perpendicular, no? So this magnetic field is perpendicular to this loop, which means they are giving us information about that angle theta. Remember, this angle theta is the angle between the perpendicular direction to the loop and the direction of the magnetic field. Since the magnetic field is exactly perpendicular, that means this angle is 0. The magnetic field is perpendicular to the loop. Okay, let's continue reading. This square coil is going to be quickly pulled from the field at constant speed. Okay, to a region where B, the field, drops abruptly to 0. Okay, so it's exactly what the figure is showing to us here. We have this square right at the edge of the magnetic field. You see here there is no magnetic field, and we are going to pull it to the right so that it's going to be in this region where there is no magnetic field. Okay, so we can draw what is going to happen. So initially we are at this scenario here, and later what is going to happen, let's draw here the magnetic field, right? So what is going to happen is we are going to take this square to the side. Okay, so we are changing with that. What are we doing? We are changing the magnetic flux. Okay, and it takes 0.1 seconds for this coil to reach the field, this region when there is no field. Okay, so let's write down what is happening here. We start with a certain initial magnetic flux. What is the magnetic flux given by? The magnetic field, the area, and the cosine of the angle. Okay, so this is our initial magnetic flux. We have the magnetic field, so I can put it here, 0.6. We have the area, that 0.05 squared. We have the angle is 0, so cosine of 0 is 1. So this is our initial magnetic flux. Okay, when we are in the scenario of the figure from the slide. Later, after 0.1 seconds, um, the coil is going to be outside the region of the loop. So we are going to be in a region that there is no magnetic field. So no magnetic field, no flux, it's going to be 0. Very well. So that's what we got just by reading the problem. Now let's see what the questions are. They also tell us what is the resistance of this wire. So let's also put this here. Yeah? The resistance for the wire is 100 ohms. Okay, so let's go now for the questions. Find the rate of change in flux. The rate of change in flux, we have it here. We have the final, we have the initial, we have the time, so we have this change. The change is this delta phi divided by delta t. Right? The final is 0. The initial is that number that you compute there, 0.6 multiplied by 0.05 squared divided by 0.1 seconds. So you put all this and you should get a negative number, of course, and this negative number is the answer for part A. And so according to what we see here, the answer is going to be minus 1.50, 10 to minus 2. Well, what is the unit? What is the unit for magnetic flux? Is Weber, right? And what is the unit for time? Seconds. So this is the answer for part A. Let's continue reading. Part B, they want to know what is the EMF and the current induced. Remember, what is the definition for EMF? The definition for EMF is minus, right? Minus n, the number of loops, multiplied by this rate of change in flux by delta phi divided by delta t. This delta phi divided by delta t we just got. We have to multiply that by n and use the minus sign to get the EMF. What is the EMF? Well, n is 100, so 100 multiplied by 10 to minus 2 gives us 1. And with the minus sign, so we get 1.5 volts. This is the EMF. What is the current? Well, to get the current, I'm going to use that the EMF is equal to Ri. I have R. Remember, they gave us, we wrote it up here, the resistance is 100. Okay, so how are we going to get our current? The current is going to be the EMF 1.50 divided by the resistance. The resistance is 100 ohms, and so you get here the number of the current. You see that how they wrote the current here? They wrote in milliamps, so we can do the same here, or you can just write it in amps. No? So if you want to write it in amps, it's going to be 1.5 10 to minus 2 amps, which, as written there on this slide, we can write as 15 milliamps. Okay, so this is part B. Let's continue now with part C. How much energy, okay, so how much energy is dissipated in the coil? Okay, we learned some chapters ago how we compute power dissipated, right? We said that the power dissipated is I square R. We have both. We have I, so we have I square, and we have R. But they don't want the power dissipated, they want the energy. But what is power? Power, so let me write here, power is energy divided by time. So if I want the energy that is dissipated, what I'm going to do is I'm going to get the power dissipated, and then I'm going to multiply by time. Which time? The delta t. Okay, so we have all the information how we are going to get this energy dissipated. Well, the power is I squared, so we have I 1.5 10 to minus 2. This is I, but we want it square. The resistance is 100, no? So I'm writing the power. So I square and R, and then multiply by the time. What is the time? 0.1 seconds. So if you put all this, and if we do everything correctly, we should get 2.25 10 to minus 3 joules, no? Because I use all the units in international system, so I get the energy in joules, and that's what you're seeing here. Part D. Well, how they solve part D in your book, it's not the way that would come to my mind. I'll just tell you quickly how they solve, and then I'll tell you how I would solve. Well, part D is using the work energy principle, no? That the work is equal to this energy. So the work is equal to the energy dissipated. And, well, we didn't read the question, so let's read. Part D is, what was the average force required? So what is the force that we have to apply here? This is the external force to remove this coil from this region. Okay, so how did they solve in the book? Well, they use the idea of work. So remember, work is force multiplied by the displacement. So if I want to find this external force, I'm going to compute the work divided by the displacement. That's how they solved in the book, and they used the work energy principle. The energy dissipated we have, so I put here this 2.25 10 to minus 3 joules, and the displacement is that 0.05. Okay, and this will give you this external force of 0.045 newtons. That's how they solve in the book. But I think it's a little bit of a stretch. It wouldn't come to my mind the idea of work. Since this whole chapter, since we are talking about chapter 20, about magnetism, induced current, that's the kind of thing that would come to my mind to solve this problem. So let's discuss that. Okay, so how I would solve this problem D. As we move this coil, the loop, from the region with magnetic field, so here we are in the region with magnetic field. As we move it, so let me make the same drawing again. As we move it outside this region of magnetic field, as we are moving it outside, what do we see? As we are moving it outside, we see that there are fewer and fewer lines crossing the loop. So here we had all these lines that you're seeing here crossing the loop, and now I see fewer and fewer. So this change in the magnetic flux, in this case this change in magnetic field crossing the loop, is going to induce a current. A current, which kind of current? The current that is going to oppose this change. So a current that will bring back those lines. A current that will bring back those lines. What is going to be the direction of this current that brings back these lines? You see, the current should be in this direction, right? Do you agree? Use the first right-hand rule and you will see that that is the case. So if you put your thumb following the current, you will see that your four fingers go into the page. Okay, so this is in red here our induced current. Okay, very well. Now let's think a little bit about chapter 20. And I'm going to remind you, in chapter 20, we said that if I have current in a magnetic field, there'll be a force. Yeah, and we saw that. Let's go back to chapter 20. Yeah? This was the kind of problem that we had. We had a current in a magnetic field. We got the force. And how did we get the direction of the force? Using the second right-hand rule. Okay? Okay, so let's do the same here. Let's use the second right-hand rule to get the direction of the force that we get, the magnetic force that we get on this loop because of this induced current. So let me make the drawing again because it's a bit messy there. So let me make this drawing again. We got an induced current in this direction here. Okay, so this is our current. The magnetic field that was already there is here. And we got this current that would create a magnetic field to oppose this change. Very well. But if I have a magnetic field here, if I have current here, I get force. What is the direction of this force? How do we get that? Using the second rule. So how does it go? We put the four fingers in the direction of the force. The palm is in the direction of the magnetic field. So our palm is going into the page. And the thumb will give us the direction of the force. So you see, here we get a magnetic force in this direction. Okay, so I'm going to write here, this is the magnetic force pointing to the left. So when the problem asked us what is the external force that we have to apply, this external force to move this wire has to be equal to the magnetic force. Now, equal because we are moving it at constant speed. Okay, so in other words, what is the magnitude of this external force is going to be equal to the magnitude of the magnetic force which we get because we have current in a magnetic field. Okay, so this is the answer of the problem. Well, now to give numbers, let us try to remember what is the magnitude of this force. So go back to chapter 20. In chapter 20, we discuss the equation for this force, this magnetic force, when we have current in a magnetic field. So what is the equation? This force depends on the current, very well, depends on L. What is L? L is the size. L is the size of the wire, the piece of the wire that is in that field. Okay, it's right at the edge, so it's in the field. So L is 0.05 meters. And what else do we have? The magnetic field. Okay, and then we have the sine of the angle. What is this angle? This angle is the angle between the current and the field. What is the direction between the current and the field? Well, the current is going up, no? So the current, induced current is going up. The magnetic field is into, so the angle is 90 degrees. So here what we have is sine of 90 degrees, which we know is 1. Okay, this is going to give us the magnitude of the external force. So put all the numbers, we have all the numbers. No? We have the current, we got that. We have L, no? L is 0.05 meters, and we have the magnetic field 0.6. So I think this is a more natural way to solve this problem, since we are talking about magnetism, magnetic force in chapter 20 and now 21. And it's also more interesting because we understand better where this force, the opposing force is coming from, and the force that we have to do to overcome this force. Okay, so this is the end of this problem.